A warm welcome to the 21st session of the third module of Signals and Systems. We have now established a much more general form of the Nyquist principle, and it is high time we now state it formally and go beyond just pulses. We have seen trains of pulses, we have seen its Fourier expansion, and in fact now we should say the following, and let me write that down right away. Now here I see a more general form of the Nyquist sampling theorem. Of course, to give due credit, it should be Shannon, Whittaker, Nyquist and so on, all of them are credited. So I don't keep saying all the names every time, but we should understand that all of them are credited in the background. So the more general form is, let Pt be a periodic waveform, periodic with period t, Ts perhaps, and let Pt have a Fourier expansion. So the Fourier expansion would be Pt is equal to summation over all k Ck e raised to the power j 2 pi by Ts times Kt. So we are writing what is called the complex Fourier series. Now we also take the waveform xt, which we wish to in principle sample, but the word sampling, as you will notice, is not really going to come in anywhere. So here we are just taking a periodic waveform, and the periodic waveform could be a train of impulses, it could be a train of pulses, but it could be any other periodic waveform, and we will see some examples shortly. So let xt be a signal with a Fourier transform, that is all that you need. And I will write the signal Fourier transform as capital X of omega, where omega is the angular frequency. We are saying the Fourier transform of xtpt is summation k going from minus to plus infinity, Ck capital X omega minus 2 pi by Ts times k. So simple. Essentially, the original Fourier transform translated by every multiple, integer multiple of 2 pi by Ts. So that integer multiple is the kth. So the kth multiple is 2 pi by Ts times k. We will continue this. Now we need to continue this. So it's a long statement. Multiplied by the corresponding Fourier series coefficient Ck, and then added over all integers k. And of course, the proof is very easy. The Fourier transform of xtpt is essentially the Fourier transform of this product, and then xt is independent of k, so we can pull it along with each of those exponentials. So we can write this down as summation k going from minus to plus infinity of this, and now our job is very simple, we have done it before. So we know that the Fourier transform of this is capital X omega minus 2 pi by Ts times k, and then the result follows from the linearity of the Fourier transform. That is a very simple proof. In fact, in a way we have already completed this proof before when we talked about the pulses, but I just formally completed the proof once again, because now we will take a very simple other example of a periodic waveform, just a pure sine wave. So let us take a pure sine wave for variety. The sine wave has an angular frequency of 2 pi by Ts, as you see. So of course, the Fourier transform of xt times pt is essentially, now it is very easy to write down a Fourier expansion of this. This is in fact already a Fourier expansion in terms of real sinusoids, but you can break it down into two complex sinusoids. So it is AC by 2 e raised to the power j 2 pi by Ts times t plus e raised to the power minus j 2 pi by Ts times t. And the Fourier transform of xtpt is so simple, it is just capital X AC by 2 of course comes out, omega minus 2 pi by Ts plus x omega plus 2 pi by Ts. Now, in fact, this is precisely what is done in what is called amplitude modulation. So, what we do in amplitude modulation, for you, a lot of you might have been familiar with what is called the amplitude modulation radio. We do hear of it even now, although a lot of systems are switching over to digital radio and so on, but we still hear of the traditional analog radio, AM radio, FM radio. It is still there, it is very much there. And amplitude modulated radio is exactly what we are doing. So, for example, xt could be say a speech signal. So, let us take a situation, let us take some concrete numbers here. So, for example, xt could be a speech signal, and let us draw some spectrum for the speech signal. A speech signal typically has components not more than 4 kilohertz. So, on the angular frequency axis it would be 2 pi times 4 into 10 raised to the 3. So, some spectrum, do not take the spectrum too seriously, some spectrum. Of course, it is going to be symmetric around 0, it is a real signal, conjugate symmetric. And let 1 by Ts equal to 10 kilohertz, just as an example. So, we need not be, again 10 kilohertz is rather low actually, but still it is all right. Let us just take it as an example. What would the spectrum of xt times pt look like? Let us see. Now, it would look something like this. You would have to center this of course around 2 pi into 10 raised to the power of 3 and move the whole spectrum so that it lies around this. So, 10 minus 4, 10 plus 4, that is from 6 to 14. So, here this would essentially be AC by 2. So, it is scaled up by AC by 2, up or down does not depends on the value of AC of course, and this is again the one shifted backwards. So, if xt is a speech signal, then this 10 kilohertz that we took was actually what is called the carrier. So what do we do typically in amplitude modulation? We aim to multiply the original signal which is to be modulated with a carrier, and a sinusoidal carrier is the most desirable. And when we multiply it by a carrier, the spectrum gets shifted forward and backward by the carrier frequency. That is what is happening here. And as you can see, if the carrier frequency is large enough, these shifted versions do not reach 0 at all. They should not. As you can see here, they are beyond 6 and beyond. Good. So, this is the spectrum of the amplitude modulated speech signal. And of course, you have a 10 kilohertz carrier. So, this is a surprising form of course, a lot of books do not write it like this. They do not write this as an example of the Nyquist theorem. I am just, in fact, that is why I am intentionally restating Nyquist theorem now a little more technically. So, if I have a pure sinusoid which essentially has two complex exponentials, what you are doing in applying the Nyquist theorem here is essentially to carry out amplitude modulation. And in fact, this also tells you how you could carry out amplitude modulation not by using a sinusoidal carrier, but any other periodic waveform. So, for example, you could build an AM signal as follows. You could multiply it by that train of pulses that we have been talking about all the while in the last couple of sessions. And then you could use a system that isolates not the 0 frequency part, but the part around the carrier. You see what I mean? Let me say a little more about this in the next session. Thank you.